Hi, in this video I want to explain very quickly what StatsX is and its main features. This will be a very superficial overview. As soon as I finish the tutorial series on Inventory X, I'll start a very detailed tutorial series for StatsX as well. So, the project I opened is the same one from the Inventory X tutorial series. I've only added the bare minimum required from StatsX to explain it. We're talking about literally 5 or 10 minutes of implementation. Let's start with attributes. While abilities can be cast by all objects through the StatsX world subsystem, attributes require the StatsX stats component base. To define an attribute, you simply need to call the initializeAttribute function and use a gameplay tag as an identifier. By default, it is replicated and automatically clamped through the overflows boolean. If it is enabled, the attribute's current value can go below 0 or above the max value. Attributes can be added or removed at runtime. And I'll mention this now, but it applies to all StatsX replication. Push replication is used, but choosing the dormancy settings is up to you. The plugin reaches almost 100,000 lines of code because it has many features and is extremely performance focused. There are many functions to explore. In the tutorial series, I'll try to show the use case for each one of them. Regarding modifiers instead, modifiers are temporary or permanent entities that alter the max value through typed operations. The calculation formulas are fully customizable and support a hierarchical override system. By default, the formula defined in the project settings is used as the base configuration, which we'll look at shortly. If the formula field is overridden directly in the component, that value becomes the source of truth and takes priority. Finally, each individual attribute can have its own custom override, allowing you to define completely different calculation formulas for every attribute if needed. Variables are defined through gameplay tags. Pay attention to the root tag. Do not use the payload root for variables. The payloads root is dedicated exclusively to event payloads. Regarding the onAttribute changed event, I bound one before the server and client split so that it gets called on both sides. This way, it behaves similarly to a multicast event, which is exactly what I need here to update the player's movement speed based on the movement speed attribute. Now, let's talk about abilities, the core of this plugin. In StatsX, abilities are called status. They are designed to be extremely performance-oriented. Bit packing is used wherever it provides a performance improvement, and a blob memory system is used, which works efficiently with the garbage collector. While GAS stands for Gameplay Ability System, StatsX could be described as a virtual machine ability system, because every ability is precompiled into a set of instructions that are executed sequentially by a small, customer virtual machine. Each instruction is 16 bytes in size, optimizing CPU cache line usage and improving execution efficiency. The first main step is creating the immutable game statuses data asset. This data asset maps the gameplay tag identifier of each ability to its corresponding assets through a soft reference, allowing them to be loaded either asynchronously or synchronously. Once the data asset has been created, you need to go into the project settings and assign it to the correct field. Now, let's take a look at how abilities are created. Abilities are data assets that are far too complex to create manually. So we use the dedicated editor tool to create them. When you open it, it should feel familiar. There is a graph and there is the details panel. You will work with it in a very similar way to blueprints, but with the difference that it is much faster and the performance is exactly the same as C++. This is because the asset itself is editor only, and the resulting ability is just a set of C++ instructions for the CPU to execute. Currently, there are around 140 nodes available. However, custom nodes are also supported, including async ones, and they are very easy to create, but they can only be created using C++. For Blueprint users, it is possible to create specific objects and call them through the custom action and custom check nodes, somewhat similar to state tree tasks. So, after assigning a gameplay tag to the status, if we save it, a JSON file is automatically generated inside the StatsX plugin folder of your project. Every time you save, the JSON file is updated. This file is your ability. It contains every inserted node, variables, and settings. This is extremely useful for source control and internal company database, and of course for sharing abilities with the community or even between your own projects. As you have seen, with a single click, you can choose the JSON file to import, and everything is automatically configured according to the JSON data. By clicking the Compile button, the data asset for this ability is generated and it is automatically added to the immutable game statuses map shown earlier. To avoid creating issues by deleting things unintentionally, I decided to keep the deletion process manual. For example, to delete this status, I first remove its reference from the editor and then remove it from immutable game statuses. Now let's look at some very basic statuses to understand the concept. There are 5 types of nodes: flow, check, action, pure, and event. Flow nodes, the blue ones, are used to control the graph execution flow. They can be async, support multiple branches, and can pause or resume execution. Check nodes, the yellow ones, are used to perform checks. They are meant to ask questions before executing actions. They have a true and false branch, or you can create switches. Action nodes are single fire and forget actions. They execute what they need to do and then continue straight ahead. Pure nodes, the purple ones, are getters. They are used to retrieve data such as getAttributeValue, getCaster, and getTarget. Event nodes, the red ones, can be either functions or events that can be called both externally and from inside this editor. Variables are defined through gameplay tags. Pay attention to the root tag. Do not use the payload root for variables. The payloads root is dedicated exclusively to event payloads. To call a variable in the graph or to set it, you use getVariable. By specifying the identifying gameplay tag in the detail panel, it will be typed with the value with which it is defined. Returning to the flow node, these are very important. Some flow nodes, but not all of them, set the status instance to active. Normally, a status is created, executed, and dies within a single frame. But a flow node can transform it into an active instance, and the status will persist for as long as intended. For example, in this case, the status will remain active on screen for 5 seconds. An active status will automatically be inserted into the casted statuses container of the caster actor and into the received statuses container of the target actor. And it will, of course, be automatically removed from these containers when it ends. Additionally, there are bindings available in the component for the status lifecycle and updates, so they can be connected to the UI. The stacking policies should cover every scenario, from simply adding stacks when the status is already active and is recast or received again, to resetting timers, rejecting it, and so on. Now, regarding prediction, it is possible to choose none, logic only, cosmetic only, and full. A status that sets full, if called through prediction and whitelisted, will be executed in prediction until it encounters a server-only node. At that point, it reconciles with the server, and the server authoritative version will continue carrying the state forward. If the status is set to logic only or cosmetic only, it will execute in prediction only the nodes marked as logic or cosmetic. All of these features can also be implemented in the custom nodes that you can create. There are 140 nodes that you can use as references for how to create your own. Now we are looking at the execution of the status with prediction. Notice that when pressing Shift, the input is received instantly despite having 1 to 2 seconds of lag. I want to point out that implementing everything we saw in the video took only a few minutes. The VFX is just the first one I found available. Now instead, we set the prediction to none, so we can see the difference between a laggy environment with prediction enabled and a laggy environment without prediction. Now, before moving on to the next status that uses events, let's take a look at the project settings. Here we find StatsX runtime, which exposes several configurable parameters, the mandatory whitelists required to use statuses and events in prediction, and other useful settings. And we also find the StatsX performance menu. This section is exclusively dedicated to performance monitoring. For each area, a backend is defined. While the areas cannot be changed, you can choose which backend you want to monitor. All Unreal backends are available, such as Insights Trace, CSV Profiler, and CycleStats. After changing a backend, you need to recompile the project for it to become active. When you ship your title, remember to set it to disabled before shipping. By default, I set it to have no backend enabled because not all Blueprint users know how to compile, and I didn't want to add even a small performance overhead to their game for something they might never use. So, now let's take a look at another status. This status is intended to represent the beginning of a fireball or any projectile, really. I'm using a casting node which doesn't have any actual functionality of its own. It's simply an organizational node, much like a sequence node in Blueprints. It's not like a loop behavior node, which has its own clearly defined mechanics. This way, I check whether I have enough mana to pay the fireball's cost. If I do, I pay the cost. If I don't, the status ends within the same frame. If I successfully paid the mana cost, it means I reach the uncompleted branch of the casting node. In this branch, I play a montage, which is an asynchronous node. As soon as the command to play the montage is sent, the next node is executed immediately. The next node is probably going to be one of your favorites. Wait for events. Wait for events has only one parameter, a gameplay tag container, which is the list of events to wait for. This doesn't mean that all of the events have to occur together. You can specify one or multiple events, and whenever one of them occurs, the corresponding event is triggered. The status remains alive as long as there are events being listened for. The onEventTriggered node contains the logic that executes when an event is received. You place one of these nodes in the graph for each event and assign it a gameplay tag so it can identify which event it corresponds to. In this case, I place the event call inside an animation notify. As shown on screen, you can trigger the event either as predicted, if it has been whitelisted, or as non-predicted. You can attach payloads to events and have them automatically matched with the gameplay tags of the variables in the receiving graph. However, it's important to use the payloads root when creating payloads, and the variables root when creating variables. Both entities are used in exactly the same way through the getVariable and setVariable nodes. The status is predicted correctly, making it feel instantaneous even with 2 seconds of latency. In this example, we're also looking at the client's authoritative reconciliation with the server. The client is spamming the attack and consuming mana for as long as it can afford the cost, while the server corrects it and restores the authoritative state. This is actually a good sign because it shows that reconciliation is working properly. However, the issue is that this status uses the rejected stacking policy, which means that if the status is already running, any new attempt to execute the same status is rejected. The server handles this correctly, but the prediction system in VR 1.5 completely ignores the stacking policy. In this latest V1.5 release, which came out just a few days ago, I implemented prediction from scratch for a specific subset of features. V1.6 will complete the prediction system by fixing the issue demonstrated here and introducing custom mutations, allowing StatsX to predict behavior beyond its built-in feature subset. It will also introduce many other features, including InventoryX fragments, making it the biggest StatsX update so far. Now let's take a quick look at custom nodes. First, they need to be defined in the editor. Essentially, we create a JSON representation of the node, which works exactly like the graph's JSON. You can import and export it just the same. The JSON is created through a context menu here in the editor. We can add as many exec input and output pins as we want, such as a non-completed branch or any other execution path. We can also add input and output parameters. The rest of the settings are used internally, so you'll almost never need to touch them. The only exception is the flags, which can be useful in certain cases. So, if we've added parameters to the node, we're required to define the bit layout. The bit layout automatically bit packs those parameters into the node's instruction for us. It tells the compiler where each value will be stored. If you run out of space because the node has many input or output parameters, you can add additional slots using the continuation slots button. Each input also carries 2 bytes of flags, which the compiler uses to determine from which of the 3 memory spaces the node should read its data. The logic that defines what the node actually does must be written in C++, but there's no need to modify the plugin itself. There are a few rules to follow, but essentially all you need to do is create a function inside a specific namespace. From there, you can retrieve the parameters you've defined for the node using functions such as extract bits slot 1, bit 24, and so on. Once you've extracted the parameters, the function executed by your node can do virtually anything. As the final thing, let's take a look at the asset definition of an ability, so we can understand why it is impossible to create it manually without using the dedicated editor. At the top, we have the status unique settings. the hash definition, and the memory calculation required for this status, which is pre-computed by the compiler in order to avoid wasting runtime performance. Below that, we have the array of instructions executed by the CPU, 16-byte instructions designed for excellent performance. As you can see, everything is bit-packed. Each instruction contains all the inputs, outputs, the memory location where any rules are stored, and the flags for that instruction. Everything is organized to achieve maximum performance. I'm curious to hear your feedback. Both positive and negative feedback are essential to improving the product and making it better suited to your needs. I look forward to your comments, either here or on Discord.